Finally, we can get our design moment capacity by multiplying by phi. However, you may remember that phi is 0.9 for tension-controlled members, steel yielding in ductile fashion, and 0.65 for compression-controlled members, when the concrete is crushing suddenly. This significantly affects our capacity, so we must confirm that the steel is in fact yielding. So this directs us to table 21.2.2, and in order to read this table, we need to calculate an epsilon t. And in order to do this, we first need to calculate c, our distance to the neutral axis. The code gives c equals a over beta 1, where beta 1 is 0.85 for less than 4,000 psi concrete. So we get a c value of 2.28. Now we can use similar triangles, which I've drawn next to the section here, to calculate the tension steel strain, assuming the concrete compresses to its maximum allowable strain of 0.003. And this value also comes from the code. So we have 0.003 on this side. We know their distance to the neutral axis, and we know the distance to the tension steel from the neutral axis because we also have our D1 value, and we can use similar triangles here to calculate epsilon t. Therefore, at a max concrete strain of ECU is 0.003, our steel would have to have a strain of 0.03, which is greater than its yield strain of Fy over E, then its yield strain of Fy over E of 0.0013, which I put here. And we need to calculate that as its yield stress, specified yield stress over its elastic modulus, ES. And that'll tell us when it's going to, the strain at which it's going to yield. And because the strain for this section, the epsilon t for this section is 0.03, and that's greater than 0.0013, we can confirm that the steel would have to yield before the concrete crushes. And our section is tension controlled, so phi equals 0.9. And with this, we can calculate Mn and compare it with our ultimate strength, Mu. So we have our design moment capacity. It's going to be phi Mn, which is 257.4 kilonewton meters.